Yeah, so I'm Arno. I'm always amazed how beautiful a country Norway is whenever I come here. I am from ThinkCell. We are in Berlin. I'm the technical guy there, and well, one of the technical guys, the head technical guy. I'll be talking about iterators. Iterators have been with us since the Stone Age of C++, and there is still conceptually something weird about them, and I'll tell you what that is. Originally, of course, they were modeled after pointers. So people were doing C, and C had arrays, and they had pointers, and they were pointed objects, and they just transferred that to modern C++ with data structures, and they said, well, we now have something like pointers, but we call them iterators because they're not all just pointers. Now, iterators can be elements, right? So if you have a vector here, 3, 2, 1, 3, and you calculate the minimum element of this vector, you get an iterator back, and it's pretty clear that that iterator means an element. It points to this element. It means an element semantically. It's pointing at the 1. But it can also mean borders between elements. So if you have an upper bound of a vector 0, 0, 1, 1, then, and you calculate the upper bound of 0, you also get a pointer to this, or an iterator to this 1. But in this case, really what it semantically means is the border between the zeros and the ones. It separates these two. Now we have ranges, and ranges are really anything that has iterators, at least according to the standard. So you can write for loops. Ranges come in 2 distinct flavors. One are containers. Containers own their elements. They have deep copying semantics. Usually takes then O of n to copy. And they have deep constness. So if the container is const, you can't mutate the elements. And there are also views. Views are kind of references to containers or to other views. They reference their elements. They have shallow copying. So you can usually copy an O of 1. And they have shallow constness. If the view is const, that doesn't mean that that directly has any effect on the elements. Quite similar to iterators, where you have a iterator that is itself const. It may still mutate whatever it is pointing to, or pointers behave the same way. Now here is the prototypical view. It's essentially just a pair of iterators that puts these 2 iterators together and offers a begin and an end that just passes out these iterators. Now, what does that allow you to do? Well, with iterators, things kind of get a little bit wordy because quite frequently you're passing in these pairs of begin and end. And with ranges, you can do this quite a bit more succinctly. So you don't have to mention begin and end quite as much. Now, the last thing here, that one, is we can still eliminate even more because what we're really doing is we're eliminating duplicates. And I want to ask you, there's something wrong with these 2 lines. Subtly, conceptually, what is it? Imagine you have, yeah?
The iterators are into different things. The iterates and arrays.
No. So your range unique, the range unique will give you something back that is iterators into the original sequence. So they are going to be compatible. That's going to be okay. Maybe it should be end and end. Maybe it should be end and end. Well, no one ever pointed this out. I've been having this talk for quite a while, but yes, probably it should be end and end. Something else, even more. But the comparators. Sort sorts by less. Unique removes by equal. If these don't agree, this code is wrong. So it's really, whenever you're writing this, that's why we have this in our library, and I'll give you the URL at the end. You really want to write this if you want to have some sort of abstraction in your code, because you have to make sure that the predicate that's used here is the same predicate that's then later used for the unique. Otherwise, it doesn't work. Right? You first need to sort, and then you need to unique. And yeah, you have to turn around the less predicate, but it's okay. But you should still use the less. Okay, then there are other views, range adapters. When you are writing without range adapters, you want to find a particular value, you use just ranges find, and it returns an iterator to the first element. Now, let's say we want to do something very similar. We have now a pair, not of numbers, but we have a pair, not just a single number, but we have a pair of a number and a character. And we want to still search the 0, but in that case, in the first part of that pair. And if you do that, the syntax, as you can see, is very, very different. You suddenly need to use range if. You can't use range anymore. And your 0 is also completely elsewhere, somewhere in the predicate. Now, that's kind of ugly, right? So the problem is that the projection, where we basically turn the pair into its first element, and then the actual search, the comparison, is lumped together. Is to lump together in this predicate here. And while here, there's essentially just this find implies that comparison. But it's operating only on that number. It can operate on the first. So what do? Enter the transform adapter. We separate these two. We first just say, okay, the vector gets transformed into a sequence of numbers. And it's happening lazily. Who's using ranges and views and stuff on a daily basis, basically? Still surprisingly few, I would say. I'm assuming you're all doing C++. So these ranges are very, very useful. I mean, for us, it's like great abstraction. It greatly simplifies the readability, improves the readability of the code. I would highly recommend using them. So here you are turning the vector into a sequence of numbers, and then you find in that sequence of numbers your 0. Now, you don't pay pretty much anything because this is all lazy, right? This doesn't do anything. It just puts together a little object. It doesn't copy anything. It just references the view's transform. So you only pay for what you dereference, and you don't allocate anything on the heap. Now, if you do this, you say find if. That's the old syntax. You have your predicate, and then you call second on it. Of course, you get the corresponding element, you get an A. Now, what happens if you do the same thing with our newfangled transform? Well, this doesn't quite work because the iterator that you're getting back from the find, fairly enough, points to ints. We are running it on a sequence of numbers. So you can't just call second on it because there's no second. What we need to do is kind of peel off this transform. And the way you do this is call .base, and then that iterator is basically transformed. It's revealing its inner self, which is an iterator to these pairs, and then on that inner self you can call second. So this is really what's happening. You have an iterator here on the 0, it gets turned in an iterator onto the pairs, and then the second one is taken. Okay, ranges find returns the iterator in role of an element. So the base that you call must preserve the identity of the element that you found. Otherwise, you get a completely different element. That's not helpful. Now, if you, for example, run ranges upper bound on a similarly transformed range, then there's also a .base call. And this .base call has to preserve the identity of the border. Because remember, upper bound semantically gives you a border. So the .base has to preserve the identity of this border, which it does. So here, this is the base, the iterators, the element stays the element, and this element, which really means this border, gets transformed into that element, and again, the border is right before the element that the iterator is pointing to, which is the semantics that the iterator has. Okay, let's look at a filter adapter. That's kind of the second frequently used adapter. It does what the name says. It filters out certain elements from its range. So you have the filter, and if you filter here by second should be B, then you only get the 2 B elements. Now let's transform this again. So you have a transform of a filter, and which again projects the result onto the B, so you got a 0 and 1. And then we run find. So now we have this stack. We first have an iterator pointing to a 0. Then we do dot base, and is now pointing to the 0b. We unwrapped the transform. And now we unwrap the filter, and then it's pointing to 0b in the complete range. Now, range is find, again, is an iterator in the role of an element, and that element, this 0 here, came from that 0b. Now, that's different than running the initial find on the whole sequence. Then we would have found that guy. But that's okay, because that's the semantics of the filter. It just gives you this iterator back, which has the b, so that identity is preserved, is correct, is fine. Now, let's do the same thing, but for upper bound. We again transform, then calculate the upper bound. Now we have an iterator that's pointing here. It's pointing now to the filter, to the unfiltered to the untransformed version, and then it will go to the original vector. Now we had the meaning here was a border between these two elements, and now the meaning of this iterator here is a border between these two elements. Is that okay? Not really, because this element, it's not really clear if you have a filtered sequence and you determine any sort of boundary in that filtered sequence. You say this goes on this side and that goes on that side. Suddenly the undoing of the filter adds elements and you don't really know on which side they should go. So this is really not well defined. If you write this in a program, it would probably be wrong. Now, you could say, well, don't do this, right? You have to understand that that doesn't work. Okay, let's keep going. Let's look at the reverse adapter. Again, we turn around the elements lazily, and we play the same game. We run transform of the reverse, find, now we have that element, and then we peel off basically the transform, so the 0b should probably point at that guy, because this is the corresponding 0b. And when you turn it around, that's still the 0b, and the iterator should point at this guy. So we have it right for elements. Okay. Now let's try for lower bound. So in this case, we have, again, the same iterator. We get the same iterator back that we got for find. It's now pointing here, which means this border. It's now pointing there, this border. And it's still pointing there. Oops, the border should be over here, because we separated the ones from the zeros. When we undo the reverse, it should separate the zeros from the ones. Now, this should be the outcome of the base call. We should have turned the iterator into a different iterator based on how we got this iterator originally. But that information is gone at this point. We don't really know anymore. So we would need kind of two different bases, but we only have one. So before we look at how we solve this problem, let's see how why the reverse adapter has this problem. How does this come about? And we look at the implementation of the reverse adapter. It has a base iterator. It has an increment that really does a decrement, and a decrement that really does an increment. So far, so easy. And the begin and an end is end and begin. Okay, that's pretty clear. But the iterator at begin of the reverse stores the base end. When you dereference that iterator, you don't want to dereference end. You cannot dereference end. You have to go one before that. So you have to calculate base end minus 1 and dereference that. Okay? Now, the same thing at end. The end stores begin. And now we say, oh, when we dereference, we decrement by 1. It's like, oh, we are iterated at begin, and then we decrement by 1. But no, the end will never be dereferenced. So we don't have any problem. So here, if the iterator is to end minus 1, then we are exactly, the begin plus 1 is then stored internally. And then we subtract 1 again, and we get begin, and that's exactly right. So this is our dereference. This is our dereference. We need to implement dereference with decrementing by 1. So here I did it. So if we call base, because the iterator is the dereferences iterator minus 1. So this is the base. This is the base for the element. It has to do 8 minus 1, because that's what we dereference. But the border is still it. Begin has to map to end, and end has to map to begin. So there's no decrement. And this creates that discrepancy by 1. Okay, so what is the, if we now look bigger, what is the scope of this problem? We now saw it with the reverse. Let's see where else that problem may lurk. Now, if an adapter changes the order of elements, you could have a crazy adapter like sorts or does something, then the base of elements is always going to be well defined. We have a corresponding element in the base range, but we don't have a border in general because we jumbled these elements around. So the border is a meaningless concept in this case, going from, you can't map one border to another border. If you, for example, had a sort adapter. The reverse adapter is special because everything changes size. We turn everything around, then the base of the border is well defined, but it's different from the base of the element. Now, let's say we remove elements. We already had this with the filter. Then these elements may collapse, and then the base of the element is still well defined. Whatever we have in the filter, we can always find the original element back, but we can't do this for the border. It's ambiguous. We already saw that with the filter. So that is for filter, sorted intersection, sorted difference. There may also be an adapter that adds elements. Now, interestingly here, it's exactly the other way around. If you have a border in the original one and added elements got added, then there is still a corresponding border in the original sequence. Because you can just remove all these elements in between, the border is still a border. But for elements, that's not true because we added elements. You may be pointing at an element that just got added. So in this case, the base of borders is well defined. The base of elements is not. Okay, so what do we do about this problem? The least we have to do is we have to separate functions, border base and border element. These can't be the same functions. We need to be able to say, what kind of base do I want? Do I want a border base or an element base? It's a small change, but there's no safety against the wrong choice that you could make. Now, we can also go one step further and say, is the concept of an iterator really what we have in our head? And I would claim no. I would say they're either elements or they're borders. And in the program, we should say whether they are borders or they're elements. What do we mean? And then we can just call .base. If these two things have two different types, base would always do the right thing. Now, the question is, do iterators really have assigned roles of border and element? Can we tell? Can we look at our code and say this iterator is a border, this iterator is an element? Can you do this? Well, luckily, we had 1 million lines of code lying around. And we just took a look. And we classified each one of them into either border or element. So let's see. We did a find. We checked for find. And find produces, we had almost 300 finds. 200 of them, actually, interestingly enough, that's this classification we also did, they were only looking for a single match. We're not really interested in multiple matches. We knew that there would only be one thing to find. So it's not like we found the first one. We found the only one, 201 times. One actually had a border role. So this, you could call a trim, really. You found something which it's really the reverse is true, where you have a certain prefix that does not fulfill your role, and you want to cut it off. So that's really more like a trim. Now, there was also one other case where you got the border afterwards. So you actually were finding an element, you wanted to get the border after that one. That is essentially trimmed from behind. All the other ones had element role. 98 times we wanted the first match. 7 of them border role, 5 the border after, everyone else element role. Now find if, similar story. 67 single ones, all element row. The borders are in vast minority. 75 times first match, 3 of them border, everything else element. Lower bound. The first twice, we had no further use of the predicate. So this was clearly a border. But 89 times, actually, the predicate that we stuck into the lower bound was used afterwards on that found element to check whether that element is really the one that we want to look at. This is really a binary search that we did. We found an element. We did not find a border, we found an element. And 19 times, that was actually also the first match. So that was basically a range of items we wanted to find. Upper bound, similar. Interestingly, you're never interested in the element at the upper bound, because that's basically outside of your, lower bound, upper bound is the equal range. And you always want to find something inside the equal range. Outside of the equal range, not that interesting. So it was either a border or it was the element inside the equal range. So I would say iterator instances have these distinct roles. We've seen this in our code base. Empirically, it's true. And iterators were always ugly. I mean, how many C++ books have shown you this picture where there's begin and then there was this ugly end going, like fell off the range. It's like so ugly. Let's make it nice and symmetric. You have borders and you have elements. There's no element up here. There's just a border right there. Now everything is nice and symmetric. Now, there's another problem or another pet peeve of mine that I always have to, the find gives me end. Why does it give me end when something has not been found? I mean, it should be singleton, right? Like optional. So, because otherwise we have to mention this range twice, which is particularly ugly because now we have all these range adapters. We produce expressions much more than giving things names. We just have expressions, and you don't want to mention things twice. So why can't I write this? Okay, you just have an iterator and it's nullable. So you can check if you can do an explicit cast bool on it. And then it will tell you, am I pointing something or I'm not pointing something? And not to point something is a pretty clear concept if you're talking about elements. Either you're pointing at an element or you're not pointing at an element. So why not make it simple? The border is, again, like an iterator, but you can't dereference it. What does that mean? You cannot dereference a border. It has an element before and an element after. And you have to decide, you want the one before or the one after. Clearly, begin and end are borders, right? Because we are talking about the delimitations of the range. And also, all the iterators that go into algorithms are, in fact, borders. It's always this begin-end pair. So it's all, here it starts, here it ends. An output iterator, a little bit old school, but output iterators are conceptually borders because you are really delineating what is the end of your current range, and then you just add on to that. Now, for the iterators that are returned from algorithm, it depends on the algorithm. Here are the algorithms that return borders. Mismatch search, lower bound, upper bound, equal range, partition point, unique. Now let's look at the element concept. Elements are like iterators, but they're never end, and you cannot plus beyond the last element. You shouldn't. And you can now go from the element to the border before or the border after. And we have find if and max min element. These are the two algorithms that I found that are clearly returning elements. And maybe we need a range of elements so that you can, when you do a for each, you can actually get the elements if you don't want to get borders. We should also make the elements nullable so that if looks nice. It would be compatible with pointers. So pointers are clearly elements. And so we make them convertible to bool. And the null state is reached through value initialization. So you can just default value initialize them, and you get a null. And any functions that return an element should we really return a null instead of end so we can do the if? Now, if we already go there, we can go one step further. We can say, the find if I classified into, do you want the first element that satisfies the predicate, or do you want the only one that satisfies the predicate? Of course, the code in optimized code is the same. But still, when you read the code, it is very interesting to know whether there are more elements or whether the programmer expects that element to be the only one. And of course, in debug, you can just put in check code that verifies that that's actually the case. So it's a valuable information to have. And at ThinkCell, we have this throughout the code base. You always have to say, what do you want? Do you want a unique match, or do you want the first match? And we can also introduce a trim left, trim right that returns borders. So you can also, they say, what do you want? Do you want elements, or do you want borders? Now, lower bound should really get a bunch of companions for doing binary find, because binary find is such a frequent operation that it really should be a single function call. And now we have the null, so it's very easy to find out whether you found something in your binary search. And again, you have the unique, you have the first and the last variants of that. And yeah, remember, you're never stuck with elements. You can always use border before, border after to convert. And the unique functions assert. Now, the idea is, of course, to, as I said, for this nullable iterators, the idea is to mention range only once. And we can, one case where we actually would need to mention the range more times is if you want to use the border that you got, for example, to cut off a part of the original range. So you really want the prefix of the range up to your border, or you want the suffix from that border to the end. And it would be nice if you could just tell the algorithm not to give you an iterator back, but the prefix or the suffix. Well, why not do that? So here it is. You have a lower bound, and you can specify, I want the border back. And you get a border back. You could say, well, I want the prefix, return take, and then you get the prefix, or return drop, then you get the suffix. If you want actually the elements, you could also specify that. You get a border, so you can directly say, don't give me the border, give me the element before, or give me the element after. Now, here is the whole zoo of things for algorithms returning elements. There's actually one missing, which we have also, which is return bool. Tell me if you found something. That's quite frequent in binary search. You're not even interested in the element. You just want to see what it's there. So you could say that's another one. You can say I want my element, or I want my element or nothing, or I just want the element. That means I'm not expecting a null here. Very, very frequently, you would write assert blah, 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 not end, right? Because you're not, well, you expect it's not end, it's being found. Well, why not write that in your function call? You just annotate your function call. And here again, for you to get the adjacent borders, in case they're not there, which does it happen? Yeah, it does happen if you don't find anything. Right, then you have to pick a border. Do you want the begin or the end? So you didn't find the element. What's the alternative? And here it's similar for basically suffixes and prefixes. We could also say, well, if either the element, and I want the element, anything that goes up to the element, not including the element, or including the element, again, suffix or prefix. Or you can say, well, if you don't find it, what do you want? Do you want an empty range, or do you want everything? These are typically the two choices you have. This is how these specifications are actually implemented. We have these little structs, and they are essentially saying, well, what happens if I found an element? How can I pack it? How do you want me to package this thing? And you can specify, for example, by calling tctake, or when you don't have an element, you just take, for example, from the begin, and then it's type compatible with in the output, so you can get a single type. But that would then mean, well, you take everything up to begin, which is empty. So that's why it's or empty. All right, that leads me to the end. So iterators are modeled after pointers. They were originally quite a low-level machine concept, or quite derived from a low-level concept. And I think it would be good to have something that has stronger semantics, elements and borders. And I think we already think in these terms. We don't need to reintroduce them. It's nothing fundamentally new, but we don't have it in the language. We can't express what we already have in our head, and arguably that's always bad. And for some functions, it's needed for correctness, that base function. The ThinkCell range library implements lots of that. So elements are nullable. We have these refinements, return specifications. What we don't have yet is you specify whether you want an element or a border, but we don't have it to have a distinct type yet. That's something that we still want to do. But yeah, so thank you very much. And of course, I wouldn't be here if you wouldn't be hiring. There's some leaflets outside. Thank you very much. And if there are any questions, go ahead.